welcome to tutorial 4. In this video, I'm going to explain all the solution for the given questions. So for question 1, we need to find the inverse matrix of A via Gauss-Jordan elimination. Here, okay, what I did was I made augmented matrix. Okay? I augmented matrix A into the identity matrix. Then as we go to the right, okay, first I want to choose -1 as the pivot to R1 plus R2, substitute R2. So for R2 we get 0, 3, 6, 2, 1, 0. I want to eliminate 2 and 2 from the column 1 based on R1. And then next, to R1 plus R3, substitute into R3. So we get 0, 6, 3, 2, 0, 1. Continue, okay. Just change the sign for R1. 1, -2, -2, -1, 0, 0. And then for R2 divide by 3, okay, divide 2 by 3, okay, to R2 we get 0, 1, 2, 2 third, 2, 1 third, 0. And then do the same with R3, we get 0, 2, 1, 2 third, 0, 1 third. And then column 1 is done. So for column 2 we have the 1 there at the second diagonal. I'm going to make that as a pivot. Okay. Just now, okay, we see the last one. Okay. I want to eliminate -2 and 2. So what I did was R1 plus 2R2 to R1. So we get 1, 0, 2, 1 third, 2 third, 0. Next, eliminate for R3 to R2 minus R3 into R3. We get 0, 0, 3, 2 third, 2 third, and -1 third. And then next, okay, I'm going to choose 3 as the pivot. Okay. I'm going to solve for R2 and R1. So 3R1 minus 2R3 into R1, we get 3, 0, 0, -1 third, 2 third, and 2 third. Okay. And then 3R2 minus 2R3 into R2, we get 0, 3, 0, 2 third, -1 third, 2 third. Now it is actually done. What I did was I just divide R1, R2, and R3 by 3 into the corresponding row, which is R1, R2, and R3 respectively. So I just jump into the final answer, okay, which is we already have the identity matrix as at the end, the left bottom, okay, and then the right side is the inverse matrix. Hence, the inverse matrix of A1 is -1 9, 2 9, 3 9, 2 9, -1 9, 2 9, 2 9, 2 9, and -1 9. Okay. And then for question 2, it's about Krebs rule. Okay. I let A is equal to 2, 5, -1, -1, -3, 4, 3, -4, -3. Okay. And then for R1, what I did was I changed, okay, column 1 with 1, 12, and -15. And for R2, column 2 is being exchanged with 1, 12, -15. A3 is for A3, the column 3 is exchanged into 1, 12, -15. And then find the course for the determinants respectively. So for the determinant, okay, what I did was I chose this, cover this, and then find this 2 by 2 determinant. So we get 2 times this determinant. For this determinant, we just cross multiply this times this minus this times this. Okay. Then for this one, 5, we need to change the sign, change into -5, and then cover it. -1 for D3, so we get this. And then for -1, just cover it, we get -1, -3, 3, -4. Okay, this. And then just compute it, we get 76. I won't explain, okay, the next time because it's literally the same algorithm. So determinant F1 A1 is 380, determinant A2 is 238, determinant of A3 is 304. So X is determinant of A1 divided by determinant of A, Y is determinant of A2 divided by determinant of A, Z is determinant of A3 divided by determinant of A. X is -5, Y is 3, Z is 4. So to validate it, I just need to substitute X, Y, and Z to one of the equation. So I get 1 equals to 1, which is true, and this is unique. Okay. Since the determinant of A is 76 and is non-zero. And then B, It's also Cramer's rule. I let A is equal to coefficient matrix. A1 is column 1 is being exchanged with negative 29, 733, negative 18. And do for A2, just change for column 2. A3 is exchanged with column 3 is exchanged with the negative 29, 73, and negative 18. Do the all of the determinants. So I won't explain further. Determinant of A is 2, determinant of A1 is 8, determinant of A2 is 10, then determinant of A3 is negative 18. This one I already explained it. X is 4, Y is 5, Z is negative 9. Just substitute the number. Okay? So those are the assumptions. So make the validation. It was found out that negative 29 is equal to negative 29, which is 2. Okay? And it's also unique since 2 is non-zero. And then for the third question, it's also about Cramer's rule, except that we are dealing with arbitrary constants P and Q. Suppose A is equal to the coefficient matrix. A1 and A2 just exchange column 1 with PQ, and column 2 with PQ. And then find the determinant. A is 1. Determinant of A1 is 3 over 5P plus 4 over 5Q. Determinant of A2 is negative 4 over 5P plus 3 over 5Q. And since determinant of A is 1, the answer is 3 the same. Okay? Sorry for the remark. Uh, we won't have no solution since determinant of A is non-zero. So for the last question, it's about eigenvalue and eigenvector. And then we need to define the linear transformation. Ax is equal to lambda x, where x is x1 and x2. Okay? Just rearrange it. We have that one important property, which is A minus lambda I. What does this mean is we need to subtract every diagonal element with lambda. Okay? So we get 3 minus lambda, 3 minus lambda. The non-diagonal element are unchanged. And then we need to find the determinant of A minus lambda I set it to 0. And then we have that. Okay, we know how to do this. Okay. And finally, we get lambda squared minus 6 lambda plus 5 equals to 0. And then factorize it. And then we get lambda 1 is 5, lambda 2 is 1. For lambda 1 is equal to 5. For lambda 1 equals to 5, we need to subtract into ax equals to lambda x. Okay. Just solve for it. Okay. And then I multiply 3x1 plus 2x2 equals to 5x1. You can use 2x2 plus 2x1 plus 3x2 equals to 5x2. We'll actually have the same relation, which is x1 equal to x2. X1 equals to x2. And then define the relationship. Okay, s1 is equal to column vector of k and k. Okay. See, then the simplest one is actually 1, 1. Okay. For lambda 2 is equals to 1, okay, we have to do it again, okay, except the lambda is now equals to 1. Okay. We just choose one of the equation, 3x1 plus 2x2 equals to x1, and then we'll eventually find the relationship of x1 is equal to negative x2, or x2 is negative x1, okay, which is the preferred way because we want to express x2. x2 is the corresponding eigenvector for lambda 1. S2 is equal S2 is trivial, so x2 is being expressed as negative k, or x2 is negative 1, 1. So those are the eigenvectors. So that's all for my tutorial. Thank you for watching.